Hello everyone. In this overview of Spike architecture, I'm going to introduce a secure root key partitioning, sharding, and sharing mechanism that we have developed and introduced to Spike's mainline. So I'll first go through a high-level conceptual diagram, and then I'll follow up with the actual source code and show you how the pieces in the diagram is actually implemented in the source code. So without further ado, let's dive in. So Spike has three main components to it. One of them is Spike Nexus. You can think of it as our secret store. So if you are familiar with tools like AWS KMS or Azure Key Vault or HashiCorp Vault, Spike Nexus is in the line of those kind of tools. It is a secure, fast, and lightweight key value store that you can keep your secrets secret. And the other component is Spike Keeper. And in a typical Spike architecture, we have multiple keepers that talk to each other in a gossip-like protocol to share the root key, essentially. And until this time, each keeper was holding a single copy of the root key. As long as you keep your keepers secure and hardened, that's fine. That's a risk that you can take because unless somebody shells into a machine that has the keeper binary or has root access to that instance, it's relatively secure again, but still we can make things even more secure. So in this workflow, I'm going to show how that is done. And the third component is Spike Pilot. Spike Pilot is the binary that we use as a CLI interface. This is our Spike Nexus, which talks to Spike Keepers to get its root key. And let's say we have Spike Pilot here. A human user can, let's say this is a human, can interact with Spike Pilot using the command line interface, CLI. Once the user authenticates and uses the pilot, it talks to Nexus using SPIFFE-MTLS to do like secret management operation, create policies, create secrets, delete secrets, update secret versions, and things like that. So it is typical secure key value store management operations. In this walkthrough, this Spike Pilot is out of the discussion because we are not going to discuss how we interact with the secret store. We'll be more concerned about how we have the root key and how we can dispatch that root key. And why do we need root key? Because Nexus has a backing store. It's configurable. Right now we support an in-memory backing store, and also we have a SQLite backing store that we can use optionally. In a typical production environment, you'd likely be using SQLite because an in-memory backing store by definition means when Spike Nexus crashes or goes away and reboots itself, then the secrets are gone. We won't want that. So when we are using a more persistent backing store like SQLite, we'll have to encrypt it because we cannot store secrets in plain form on disk. And that root key is used to seed the encryption mechanism of the SQLite database driver. So that's that. Like in a nutshell, we use the root key to encrypt our secrets. So the issue is the keepers, as their name imply, keep the root key somehow. So let's say like these are the keepers. This circle is the root key. But the Nexus down here doesn't have the root key. So this actor needs to get the root key so it can like encrypt its stuff, do its secure secret management job. So to do that, we have this workflow. So how we create and like compute the root key is each spike keeper, when it initializes, it computes a random string, what we call it as a share. Each share is like a 32 bytes of a string, and once the keeper creates its share, it does two things in parallel. One of them is to broadcast its ID and share to all of its fellow keepers. It says, hey, I am keeper number 1, this is my share. And keeper number 2, keeper number 3, all of them do the same thing. And in this scenario, we have 3 keepers, and it is right now hard-coded. But later down the line, we'll make it adjustable. Like, making it adjustable is like relatively straightforward. It doesn't change too much in the source code other than changing a bunch of constants that say we are going to use 5 out of 7 instead of 2 out of 3 keys. So we just change 2 variables and it will be set up. But for now it is constant. We have 3 keepers that share their shares. So the keeper broadcasts its share, and in the same time it fetches the shares of its peers. And this way we have, each keeper has 3 separate 32 byte random securely generated strings. And what that keeper does with those strings is to combine them in a, or like mangle them in a secure way, so that we have a uniquely random key that we can seed into like certain cryptographic algorithms. And that is done by like XORing all of the shares that we gathered. So when we XOR those shares, we create this root key. So it is the combination of all of those 32 byte keys. And since we are exclusively ORing, all those keys, each keeper comes up with the same identical root key after all of these bootstrapping sequence. And then the fun part begins. We use what's called a Shamir Secrets Sharing algorithm. Okay, so like we created the root key, and now it's time to partition the root key, and for that we'll be using Shamir's Secrets Sharing algorithm. And in our particular use case, we are using 3 shares because we have 3 keepers and we have a threshold of 2, which means any 2 shares out of the 3 shares will be able to regenerate or recombine the root key that we have. So we take the root key, and each keeper computes 3 distinct partitions out of that root key. And like I said, two out of those 3 partitions, like partition 1 and partition 2, or partition 2 and partition 3 combined, can recreate the root key that you see here. So we have these partitions, and each of the keeper also knows its ID and which partition it's supposed to have. So let's assume that we are keeper 1 and we want partition 1, and we don't need partition 2 and partition 3. So what we do is the keeper 1 securely erases partition 2 and partition 3, and also it securely erases the root key. So it doesn't have anything down here, and it only has partition 1 in its memory. So it will keep it, and this repeats for other keepers too. So keeper 2 will have partition 2, keeper 3 will have partition 3. Each keeper will have one of these partitions stored in its memory, and it will discard any other temporary material. It will securely erase it, and that's the second part of this initialization flow. And then it comes to Spike Nexus. Spike Nexus, it will wake up and it needs a root key. And by the way, all of these interactions, like this Nexus calling keepers, or for example the keepers talking to each other, all of these communications are secured by SPIFFE mTLS. So both the keepers and Nexus has their SVITs, has their binary attestations. So for example, it requires that the keeper to have a certain SHA hash for the binary. It needs to run in a certain path. It needs to be run by a certain user account and a certain group. And unless it passes all of those attestations, it won't be able to establish this mTLS connectivity down here. So all the connections across the network boundaries are secured by mTLS. You don't have to worry about somebody eavesdropping and like saving the partition and then reconstructing it elsewhere. The only person or the only entity that can see the partitions are keepers and Nexus at this architecture. Now it comes to Spike Nexus to fetch its shards or partitions to reconstruct the root key that it needs, and it does it in a kind of a loop. It talks to all of the keepers and it fetches the shards from the keepers. So in this scenario, like 2 shards are coming from 2 other keepers, like the purple and yellow as depicted by the yellow and purple color coding here, and this like teal is the one that's coming from this one. So Nexus gathers 2 shards exactly in this scenario. Like as long as it gets the second shard, it doesn't ask for the third one because it has enough material to reconstruct the root key. We use Shamir Secret Recovery algorithm, which is the counterpart of this Shamir Secret Sharding. It's like a mathematical inverse operation, which is used to recover the root key. So these 2 are like mathematically related. So by using the Shamir Secret Recovery, we regenerate the root key out of the 2 partitions that the Spike Nexus has received. And that's like the entire workflow, because once Spike Nexus has the key, then it can happily configure the backing store, and from that point on, all of the secrets that is saved to Spike Nexus will be encrypted by that root key, and it will be stored to the backing store in encrypted form. And if Nexus crashes, it will follow up this initialization sequence once more. It will talk to all of the keepers to regenerate its root key. So that's how things work, and that's mostly the happy path. And there are use cases for the unhappy paths as well. Like if a keeper crashes, let's say that this keeper is crashed and then it brought up itself again. So what it can do is it can talk to its peers, and similar to what Nexus does, it can gather 2 separate shards from 2 of its peers, like this is 1 shard and this is second shard. Then from those shards, it can recompute the root key again. Then it can repartition the root key using the same algorithm, and then it can take its own partition and discard anything that's intermediary. So it's like if Nexus crashes, we have a backup scenario to recover from. If a keeper crashes, we have a way to recover. If more than 1 keeper crashes in that scenario, like we are essentially doomed. But we can increase the number of keepers and play with the threshold number. Like we can say we have 3 shares and we need 1 threshold, which is not quite secure, but still like feasible, usable in a test environment at least. Or we can have 5 keepers and with a threshold of 2, which will give us a balance of like convenience versus security versus operational complexity. So that's our current ways to recover from a disaster scenario, and we are going to introduce like a break the glass workflow to recover later down the line as well. And in that scenario, it will be like 2 separate admins will provide their authenticity and talk to these keepers before they crash ideally, to get the shards and then save those shards securely in an offline enclave, so that when there is a need to like reinitialize system, break the glass because everything has crashed and the system cannot recover, then uh, they can enter those shards separately, and then Spike Nexus can recover from that disaster scenario, and then it can even inform those keepers saying, hey, I have recovered, I think you need some recovery as well, so get these 2 shards and then figure out how to like reinitiate your flow. So those are like for future implementation, but even at this stage, to me the system is robust enough. And let me go through the source code to show you what parts of this diagram maps to what parts of the actual source code. I'll skip this, internal trust establishment, mTLS creation, because I have covered it in other demos. You can like watch these stream of video, these series of videos to like get an idea about what's happening. So I'll directly dive into the keeper sharding logic. So we have 3 states. One of them is the error state, and this code is like work in progress. It's mostly done, but there are parts, as you can see, that have not been implemented yet. So I'll just go through the ones that are like implemented already. So for whatever reason, if the system crashes and things fall into an irrecoverable error state, it will log it, it will exit. Then we need to investigate, check the logs and see what's happening. And if the application is not ready, then we run 2 Go routines. One of them is to contribute its shard to other keeper instances, and the other is to wait for shards from other keeper instances. So let's dive into this contribution flow. So what we do here is, in a loop, we query through our peers. So for each peer keeper that we have, we ping a URL like v1 store contribute, saying, hey, I want to send my contribution to you so that you can store it. So again, we create an mTLS client using SPIFFE. I am skipping those parts. And after that, we create a random contribution. I'll dive into the details of it as well. So let me move this one a little bit so I can dig into this random contribution function. So if we haven't created the contribution before, we create a AES 265 cryptographically random binary seed, and then return that seed essentially. But if we do have a contribution already, if we do have created this one and it is in the memory of this keeper instance, we return that so that we don't mistakenly create 2 different contributions and make up the shard compute logic falsy. That's how this random contribution is executed. And the other is like storing the shard, and that is like, it's just a thread safe map storing operation. So if you dig into this shard, it's a sync map, and we just store that shard with the ID of this keeper on that map. So that is how we store our own shard. But that's one part of it. So we store the shard, but the goal of like contribution is not storing the shard, but it's also sending the shard to all other peer keepers. So for this, we marshal that shard into a shard contribution request, and then post to all of the keepers that we have listed above. And if the request fails, we wait for a while and retry until all of our requests are successful, and we share our shards to all the keepers that we know. So as a kind of a side note, This is also a work in progress. This algorithm is not ideal. We are going to convert this to a more exponentially backing of try attempt, so that we don't put pressure on keepers. So the keepers are by design really simple. So like this won't even happen. Like if I the only time this can happen is when there's a network partition, and when there's a network partition, there's no need to like try it over and over again. We can back off and like wait for a while until the network recovers, and that back off is better to be done exponentially, so that like we don't consume too much system resources. Essentially, it's basic distributed system design. So that's that one. So what we did so far is we contributed our shard to, give me a second. We contributed our shard to our peer keepers, and next up is we are waiting for shards from our peers. So, and all of the keepers mirror each other aside from their IDs, so they do exactly the same things but with different IDs and different shard numbers. So that if we dig into the wait for shards function, it is like in a infinite loop. Again, all of these loops can be optimizable. This is just the first iteration. We'll do a code review and discuss, whether we should sleep that much, or whether we can do like a more intelligent backing of algorithm and things like that. But at a high level, the gist of this wait for shards algorithm is, so we in this wait for shards method, we wait for enough shards to receive. So every time we get a shard, if you remember, we update this shards sync map, and if we have exactly 2 shards, we exit this busy wait for loop after like creating some final computation, which I'll get to that real soon. But for whatever reason, if we have like more than 2 shards, we say, hey, there's something problematic, because as a keeper, I don't want to get more than I need. So for whatever reason, if I get more than 2 shards, it would mean that I have received a shard from a keeper that I don't know, because all the shards, like, because I am one keeper, I have 2 other peers, and these will be configurable later down. Right now it's hard-coded, but it's because it's just the first incarnation of this logic. But assume that I have 2 peers aside from myself, and if I have 4 shards, then it would mean that either I get somehow the same different shards from the same peer, and I mark them separately, or there's another peer that shouldn't be there that is pushing the shard. So it's suspicious. So rather than saying like, hey, I have more shards, the more the merrier, I just raise an alert and like break the world down and say, I'm crashing and I'm logging this, and I will also audit this because this is something that I don't expect. So actually I took a note down here as well to do an audit log, because this is a security incident likely. I'm getting something that I'm not expecting. So it should be logged and alerted essentially. But regardless, like if all these checks pass, then I'll create a final key, and then I'll split that final key into what we call Shamir shares, and then I'll set my internal shard to the share that I need, and then I'll do some sanity check. I'll dive into those functions just for the sake of completeness. So let's dig into the compute final key function first. So the compute final key will loop through all of the shards that I have, and it will exclusively OR those shards byte by byte, And again, there are certain guard clauses and sanity checks, like the shards needs to be 32 bytes. I need to have 3 shards, no more. And eventually, if everything succeeds, we return the final key. And after that, we pass that final key to this compute shares function. And this is some Shamir Secrets Sharding work. And we are using the Cloudflare Circle library for those shard computation and combining. Cloudflare uses this Circle library internally. It's a well-vetted, secure, and robust library that you can rely on. So we do rely on it as well. The Shamir Secrets Sharing algorithm returns a random seed to compute its shares, essentially. But in our case, it's a little tricky because we cannot provide the 3 different random seeds to 3 different keepers without coordinating those random seeds, and things can get tricky. Well, final key is unique for all of these keepers, so we can create our random number generator by using final key as a seed. Let me zoom that part in. So it's kind of here, there is a detailed security analysis. So we generate the final key by XORing 3 different entities. So it has enough entropy in itself to feed into a random number generation algorithm. We are using that random key to feed into the Shamir's algorithm as well. But the thing is, the security of the algorithm is not depending on the hiding that random seed value. You can even see certain implementations of Shamir Secret that is using a well-known prime number because to emphasize that that number is not related to the overall security posture of the algorithm. And we also digged into Circle's implementation and how it uses that random seed, and it just uses it to create some polynomial coefficients. And even if an attacker knows those polynomial coefficients, it will be useless because without the partitions, those polynomial coefficients are worth nothing essentially. So in a sense, seeding the algorithm with the root key is secure enough in our implementation. I have gotten a bunch of questions on certain discussion groups about, how secure is this? Shall we seed a different key? Which can be optional. Let me also add a to-do item. To do, give the end user to seed their own key if they want to via an environment variable. So the end user can, if they want, optionally they can configure the key instead of reusing that final key, but that would be more cumbersome, to be honest. But regardless, when we seed the secret sharing algorithm with a deterministic random number generator that all of the keepers share, and we split the secret into n shares, and in this case n is 3, so we are separating the secret into 3 shares, and we are returning the secret itself and all of our shares as well. So that is the compute shares function that we did. Let me go back to where we are using it. And after that, we set our internal shard, which if we are the keeper number 1, we'll get the first share. If we are keeper number 2, we do the second share. And to order those keepers, we sort those keepers by their ID. And then we match, if the ID is my ID, then I get the shard in that index of that ID essentially. And there are also additional sanity checks. If after this computation logic, if my shard is still nil, I bail out and crash and log essentially. That's that one. This is set internal shard. Let me go back to its usage. And after those, we have the secret and we have the shares. So we do a sanity check using this secret. So we took the first two shares and we tried to use the same algorithm to recover and reconstruct our root key. And if the root key is not equal to the original root key, the reconstructed root key is not equal to the original root key, then there's a problem with our initialization logic, which means like we need to check. So we just crash and log this one to figure things out. Ideally, this should not happen, but still it's a precautionary step so that while adding a feature or developing this or testing this, we come into this, we can investigate. So that's that part. Let me go back to where we use it, and that's the wait for shards action that we are doing here. And while we are doing it, we also initialize a server so that we can start both listening to other keepers, sending their shards, and also sending our shard to the keepers, and also listening for Nexus to ask for a partition, which will come next. So let me go to Nexus's entry point. Again, I'm going to skip like some internal prelude, like this authentication and SPIFFE context creation and whatnot. Here we create a timer down here, and we kind of tick at every certain interval and try to talk to all of the keepers that we know of and ask for their shards. So it's inside this loop. So we have a keepers collection, and then we say, hey keeper, can you give me your shard? And then essentially the rest is like error collection, where we try to check it. If we cannot talk to the keeper, we ask the next keeper. If we cannot, then we wait for the next ticker interval to come, and we do this all over again until we successfully gain enough shards to recompute the root key. So all of these are like those kind of operations. So we post our shard request, and then we eventually receive a shard response, and then we do some check, and if we have enough shards, then we start again using the Shamir's secret reconstruction algorithm to recompute the root key. We will use the same parameters. I won't dive into the details of this, and I'm assuming it's relatively readable enough in itself. So what we do is we create a collection of shares, and we got two shares from two separate keepers in this algorithm, and I know that this can be made more generic, and I also do know that this is done with the assumption that we have two keepers. If we have more, this will be like, instead of first shard, second shard, it will be a array iteration in an index of shards. But this is right now, it's more expressive, and it's better for the purpose of teaching this essentially. So we append the first share and the second share that we got from our fellow peer keepers to this shares collection, and then we use Shamir Secrets Shares recover function to recover the secret. The one is the parameter one is means that we need two shards to recover. So recover returns a secret provided more than T different shares are given. So we need 2 shares. 2 is more than 1. So we are passing 1 to the recover function. Like I would have preferred number 2 instead of number 1 because it is more implicit that I need 2 shares rather than I need 1 more than 1 share. But I don't know, that's their decision. So we'll stick with the implementation because that's how that library is implemented. So we reconstruct the root key. So this is this reconstructed variable. Come on, is a representation of our root key, and when we marshal it binary, we get a binary representation of the root key. And again, I'll put a note here to do check for errors, because there's no error handling down here. We are assuming that we get it. We might not, the data might be corrupt or something, so it's better to have error handling there as well. Then we don't also check the size. We have to check the size of the key because we are assuming that it needs to be 32 bytes. After that, we encode the root key into a hex string representation, and then push it to our initialization logic. This encode to hex is like our business logic requirement. It's not related to Shamir Secrets Sharing, but it is how we internally store the root key for secret initialization purposes. So that's why we are hex encoding it. And when we go to this initialize function, for sake of completeness, it will initialize the persistent store backend. And when we go to that initialize backend, it will do kind of a switch between what kind of store you have. If it's in memory, to be fair, we don't need a root key at all, because when the system crashes, it's gone. But if we have a SQLite backing store, then we need to initialize that with the root key. So this initialize SQLite backing store does like a bunch of stuff. I will just look into where the root key is used, which is here. We use that root key as the encryption key of the backend config struct, essentially. And that's that. And after that, we have a database backend that has been configured to use that root key to encrypt its secret while it's storing it on disk. So that was quite a walkthrough, but I hope it was informative. Like I said, this is work in progress. It has come to a relatively usable state, but there are still some kinks to iron out and some parts to improve further upon. But as long as how but before that, I also want to show you, because I also did a write-up about how this entire Shamir Secrets Sharing scheme works. So it's down here in this address, 0 to hero dev spire spike Shamir Secrets Sharing. So I'm explaining here like what we do, how we do it. This you can see this architectural high-level overview diagram there as well, along with source code and everything else. And also I have a threat analysis about what are the attack surface, what are certain things that might be improved upon. Like, for example, if you want to use a trusted platform module, would it make sense, and things like that. So it's at the time of this video, it's in progress, but it's mostly done. But it will be on that address for you to enjoy reading. But yeah, as far as Shamir Secrets Sharing and sharding a root key into separate keeper instances so that the secret store Nexus in Spike architecture can consume them and reconstruct its root key, that's all there is to share, I guess. And until next time, keep your secrets secret.